Hey, Mrs. Weefy back for Unit 6 video lesson 11, and we are going to focus for the rest of this unit on the properties of gases and the gas laws. Now, one of the big differences between gases and solids and liquids is the compressibility, and that is the measure of how much the volume of matter decreases under pressure. Now, we said before that liquids and solids are basically condensed states of matter because the particles are fairly close together and they cannot be pushed closer together. But gases, on the other hand, the particle arrangement, they're very far apart, so that they do have the ability to be compressed. So let's take a look at this. We have a large container and we see that the molecules are moving far apart. Now notice we're going to keep referring to the kinetic energy as it's related to temperature of gaseous particles. So we see that these particles are in motion at a certain speed or a certain temperature. Now we're going to take that container and we are going to compress the air sample so that the molecules are much closer together. Now think about this. When you compress and you make the container smaller, if these particles are going at the same speed, that is, they have the same average kinetic energy, same temperature, what's going to happen to the number of collisions that you have inside the container? Let me act like Dora here for a second, and you guys think about it. Yep, that's right. The collisions are going to increase, and so therefore you're going to have an increase in pressure. And so those are the things that we are going to talk about in the last part of this unit. Now, when we're talking about gases, we have four measurable properties, and because these properties are measurable, we can make relationships between them. One of them is the amount of a gas, and the amount of a gas is measured in moles. The abbreviation for mole is MOLE, and the symbol that we're going to use in equations is N. So anytime you see the symbol N, that refers to the number of moles. Now these are things that you should be getting down into your chill, and if you need to pause, then make sure that you pause the video and take good notes. The second measurable property is the temperature of a gas. Now the temperature of gases are always measured in Kelvin because we have direct relationships with Kelvin rather than Celsius temperature. The symbol for Kelvin is a capital K, and the symbol that we are going to use in equations is a capital T. For Kelvin. If it's a lowercase t, then that would be degrees Celsius, but we always use Kelvin, and that's something that you need to make sure that you do every single time. You have temperature in Celsius, you have to convert it to the temperature in Kelvin. Now the third is pressure, and pressure can be measured in atmosphere, kilopascal, torr, or millimeters of mercury, as you had already done some pressure conversions. The symbol for pressure in equations is a capital P. And lastly, we have volume, and that is the amount of space that's occupied by the gas measured in liters. Can be milliliters or centimeters cubed or cubic centimeter, but when you're talking gas volumes, you usually have large quantities of gases because they're so spread out because of the space between all of the particles. The symbol for volume as used in the equations will be a capital V. So how are the pressure and volume of a gas related? And take a look at these two cylinders that you have here. This one you have a certain volume, and then this one we have compressed the volume. Now take a look at these particles and how they're moving, okay? And so when you see this, it looks like it's hitting, so you have collisions off of the side of the container. And so what are collisions? And that is the pressure that we're measuring when we consider the collisions. Robert Boyle was the first person to study this pressure-volume relationship. He did this in a systematic way by many experiments. What two variables can you visibly see changing in the diagram? And the one that is very apparent okay, is the size of the container or the volume. And then the other one is the number of collisions. So take a look at how many collisions we see here. And then when you decrease the volume, you can see that you have many more collisions on the side of the container. The other two variables remain constant. So remember, we have 4 variables, and we're going to talk about 2 at a time, which means the other 2 are going to be constant. So let's talk about the constants first. First, you have the quantity. So between the 2 cylinders, we have the same number of particles in each one. So the quantity is the same. The other one is the temperature. The temperature is the same, and we're going to represent temperature by whooshies, and we don't really see any whooshies here, so we haven't increased the temperature or the kinetic energy, so those particles are moving at the same speed between the 2 cylinders, so therefore they have the same temperature. So the variables then, okay, is the volume, which I've already mentioned. So we've decreased the volume, and when we decrease the volume, then we see that the number of collisions have increased. Now graphically, if we take a look at this, if we decrease the volume, let's say we go from 1 liter down to a half a liter, what happens to the pressure? Well, we see that the pressure goes from, at 1 liter is 100 kPa, it goes up to 200 kPa at a half a liter. So what did we do? We cut the volume in half and we doubled the pressure. That is what we call an indirect or an inverse relationship, where one variable decreases, the other variable increases proportionally. So if we cut one in half, the other one's going to double. If we cut one by a third, the other one's going to do what? Yep, that's right, is going to triple. Okay, we have another relationship, okay, between temperature and volume. And so again, what are the constants and what does it mean at the particle level? So we see that we have a temperature change. We go from 300 Kelvin to 600 Kelvin. And we also see that we have a difference in the size of the container. So those are our variables. So then what are our constants? And again, what does it mean? Well, our constants is the amount, the quantity. So you have the same number of particles. But then our other constant is pressure. And what does it mean to have a constant pressure? Think about this. What is pressure? Pressure is the number of collisions. So we're going to have the same number of collisions in the smaller volume as we do in the larger volume. Okay, and so what happens? If we increase the volume, then the number of collisions has to stay the same, so we have more room for those particles to move around. How is that going to affect the temperature? Okay, so the temperature is going to have to increase, which means that the particles is going to have more kinetic energy, or they're going to move at a greater speed. Why? So that the number of collisions in the bigger space is going to remain constant. So those are the things that I want you to think about, the relationships that I want you to think about. Okay, so now let's talk about the variables. So if we have the quantity is the same in both cylinders, the volume increases in order to keep the number of collisions the same, that's the pressure, then the kinetic energy, as I mentioned already, has to increase. This is a direct relationship between kinetic energy, or the temperature, okay, and the volume of the gas. Let's take a look at this graphically. All right, so here we have 300 Kelvin. When we move to 900 Kelvin, we have tripled. Well, at 300 Kelvin, we have a volume of 1 liter. And if we increase the temperature to 900, then we have tripled the temperature. We also triple the volume. So we go from 1 liter to 3 liters. That is a direct relationship, or a direct proportion. And this is called Charles' law. Okay, an example of Charles' law in motion is a hot air balloon. So, if you have propane burners inside or on board the basket of a hot air balloon. And so if you increase the temperature, then what happens is the particles are moving along around a lot quicker. It's going to inflate the balloon, and then the balloon is going to rise. So hot air balloons is Charles' law in motion. Now let's take a look at what happens when the pressure and the temperature of the gas. How are the pressure and temperature of a gas related? Well, take a look at our constants now. What are our two constants? Well, the one that has been a constant all along is the amount. So we have the same number of particles in each of the container. But then if you notice, we see that the volume is exactly the same. So if you heat up, notice the Bunsen burner here, if you heat up that cylinder, what's going to happen to the particles? Well, the energy from the heat is going to be transferred to the particles. The particles are going to increase in kinetic energy. That they're going to move around faster. As they move around faster, their temperature increases. They're going to hit more, collide more on the sides of the container, and therefore the pressure is going to go up. So our variables are temperature and pressure. So as the temperature increases, the pressure increases if that volume and the quantity is constant. And this is called Gay-Lussac's law. Now, Gay-Lussac's law is applied to pressure cookers. So if you have a pressure cooker as a sealed container, and it takes less time to cook foods in a pressure cooker because when you heat up the foods in this sealed container, the pressure increases, the temperature increases rather quickly, and so it takes less time to cook the food. However, because it is a sealed container, you could have an explosion, so there's like a little release valve right here to help relieve the pressure a little bit so you don't have a problem, a big boom. Okay, now we have an expression that's called the combined gas law, and what this does, it's really cool. It combines Boyle's law, Charles' law, and Gay-Lussac's law all together. And here's the expression. So we have P1 times V1 over T1. So pressure times volume divided by temperature is equal to P2 times V2 over T2. So what do these ones and twos mean? Well, this set is the initial set of conditions, and then the P2, V2, and T2, these are the final set of conditions. So those are the conditions after you have changed one or more of the initial conditions. So how do we use this equation? Let's take a look at some problems. Here's a problem. A balloon contains 30 liters of helium gas at 103 kPa. What is the volume of the helium when the balloon rises to an altitude where the pressure is only 25.0 kPa? We're going to assume that the temperature remains constant. That's pretty important assumption. So let's list the givens. We have P1 is 103 kPa, V1 is 30.0 liters, and P2 is 25.0 kPa. Our unknown is V2, that's what we want to solve. So we're going to use the combined gas law. That's the only equation that you need to learn. Now here's the thing, temperature is constant. So what are we going to do? We don't know what the temperature is, and we don't need to know. So here's what we do. We're just going to cross out the T's. And so our equation then is P1 times V1 equals P2 times V2. It's that simple. So you don't have to memorize 3 equations, just this one. So plug in your numbers. 103 kPa times 30.0 liter equals 25.0 kPa times V2. And we're going to solve for V2. So in order to do that, we divide both sides by 25.0 kPa. The kPa divides out, and then do your math. And V2 is equal to 124 liters, so we want 3 significant figures as we determine from the givens in our problem. Okay, let's take a look at another one. Well, before that, let's evaluate our answer. Does it make sense? So if you have a decrease in pressure, then you would expect an increase in the temperature, and that's what we saw. the volume did increase from 30 to 124 liters. Let's try another one now. What is the temperature of a 2.3 liter balloon if it shrinks to a volume of 0.632 liters when it is dipped into liquid nitrogen at a temperature of 77 Kelvin? Okay, so our givens, we have V1, T2, and V2, and our unknown is T1. So we have our, before we do anything else, remember that our temperature has to be in Kelvin, okay? And so we have T1 is equal to negative 196 degrees Celsius. We add 273 to it and we get 77 Kelvin. Oh, you know what? I didn't change that in the problem. I left it at 77 Kelvin instead of changing it to negative 196 because I wanted you to make that temperature change. But it's a good thing to note that if you would have been given the temperature in Celsius, you have to add 273 to get the temperature in Kelvin. And so our unknown is T1. So with the combined gas law, our constant, notice, is V1. And so, P. The pressure, we have no pressure, so we're going to cross out the pressures on both sides, and that leaves us with V1 over T1 equals V2 over T2. We're going to plug in our numbers, okay, as I did here. So we have 2.3 liters over T1 is equal to 0.632 liters over 77 Kelvin. Now what some of you like to do, and this is no big deal, you can do this. If you want to, you can take this T1, okay, and you can make it equal to X and then solve for X. And how would you do that? You would just cross multiply, and if you cross multiply, then you would solve for T1 or X, and T1 would be equal to 276 Kelvin. Okay, so I think I have one more. And again, does this make sense? So take a look at that. All right, one more. So a volume of gas-filled balloon is 30.0 liters at 313 Kelvin and 153 kPa. So notice we have volume, we have temperature, and we have pressure. What would the volume be at standard temperature and pressure at STP? So you have to know what the conditions are at STP. So let's list our givens. We have V1, T1, and P1. T2, the standard temperature at STP, is 273 Kelvin. Our standard pressure at STP is 101.3 kPa. So our unknown then is the volume, okay, because it even asks what would the volume be. That's our V2. We're going to use the combined gas law, plug in our numbers, and so we're going to solve then for V2. And V2 is equal to 39.5 kPa. Okay, so that brings us now to the conclusion of this video lesson, which I know was kind of lengthy, but be happy, have fun, and dance. This is Mrs. Weethy. So long for now.